So electrodynamics implies the existence of electromagnetic waves that propagate at the speed of light, and we can recover that from Maxwell's equations, as well as an identity from vector calculus. So from vector calculus, if we take the curl of some arbitrary vector, then that's just del times the divergence of that vector minus the Laplacian of that vector. So we can start by taking the curl of Faraday's law, which is this one. So take the curl of Faraday, and we see that del cross E, just using this identity, is just del times the divergence of E minus the Laplacian of E. And then we could plug in the other side for the dB dt, and we just see that it's negative ddt of the curl of B. Okay? And now we're going to make the assumption that we're in a vacuum. So there's only the fields. There's no charges or currents. So rho and J, the current density, are going to equal 0. So assume we are in a vacuum, which implies that rho is 0 and J is 0, rho being the charge density, J being the current density. So then Gauss's law just takes on the electrostatic form, del dot E equals 0. So now we can plug that into here, and we see that 0 minus the Laplacian of E is equal to minus ddt, and then del cross B is just the Ampere-Maxwell law, or the Ampere's law with Maxwell's correction, but since J is 0, that term just becomes mu naught epsilon naught dE dt. So we get mu naught epsilon naught dE dt, or negative mu naught epsilon naught del squared dt squared of E. And then these just become positive. So we recover that the Laplacian of the electric field is equal to mu naught epsilon naught, the second derivative with respect to time of the electric field. And if we define mu naught epsilon naught as 1 over c squared, since c is 1 over epsilon naught mu naught, then we see that this satisfies a wave equation of the electric field propagating at the speed of light. If we remember wave equations of the form where the 1 over squared term is the propagation velocity. So for electric fields, that propagation velocity is the speed of light. And we could do the same thing for B. So for B, we just have to, instead of taking the curl of Faraday's law, we're going to take the curl of the Ampere-Maxwell law. And since we're in a vacuum, J becomes 0. So the Ampere-Maxwell law just becomes del cross B is mu naught epsilon naught dE dt. So if we take the curl of this equation, del cross B is the gradient of the divergence of B, which is always 0, minus the Laplacian of B, is just, if we use our mu naught epsilon naught substitution, that's just 1 over c squared d dt of del cross E, the electric field. And now we see that the negative Laplacian of B is 1 over c squared d by dt of del cross E, where del cross E is just taken from Faraday's law. So that's just 1 over c squared d dt minus dB dt, which is just negative 1 over c squared del squared B dt squared. And once again, the negatives become positive. And similarly for the magnetic field, we see that the Laplacian of the magnetic field is just 1 over c squared times the second time derivative of the magnetic field. So in a vacuum, electric and magnetic fields have wave-like solutions that propagate at the speed of light. And these wave equations have solutions that have explicit form that are in a complex notation given by complex amplitude E naught, exponential I k dot r, where k is the propagation vector, minus angular frequency times the time. And then that's all in the n hat direction, where n hat is the electric field polarization direction. For the B field, we get a similar complex solution, except the propagation is orthogonal to the electric field. And the amplitude B naught, the complex amplitude, is just the electric field amplitude over C. So we can just write it in terms of the electric field, exponential I k dot r minus omega t, but the direction is now propagation direction crossed with the polarization of the electric field. So these are the solutions. And then if we want to just take the physical part of the field, just take the real part of the complex solution. And so, to give an example, just imagine we have an electromagnetic wave propagating normal to the YZ plane. So it's going that way into the page. And let's say that our electric field takes the form of E naught cosine kx minus omega t in the y hat direction. Then the electric field polarization n hat and the propagation direction, and then the cross product of those two form a right-handed coordinate system. So if y hat is our electric field direction, so it's going to look something like this. Right, where it's going that way. Let's draw it in. So that's in the, no, I just wrote X, Z here. This is X. z is going up. But if the electric field is going that way and our propagation is this way, which is the minus x direction, then the B field has to be in the z direction. Because if we have z, x, y, and then y is just the electric field polarization, and then the propagation direction, or sorry, the B field direction is just k hat cross n hat, then that means that we're going to have propagation along the negative x direction. So this is k hat, and that's negative k hat, and that'll be our propagation.